This lecture, Laplace Transform, Chapter 2 of Process Control, Laplace Transform Part 20. We have been seeing forcing functions. We have seen a couple of forcing functions earlier, the last two lectures. And today we will see another forcing function known as impulse function. So to understand this better, you should recall the last lecture, part 19, which is on pulse function. So if you recall, if I listen to that part 19, the link for that is given in the description below. If you have not listened to that, please listen to that again. If you know pulse function, it is easier to understand impulse function. So let me quickly recall the pulse function. So this is pulse function. Pulse function is one which is 0 everywhere, except for a brief interval of time 0 to h. So except at this place between 0 and h, except at this place, it is 0 everywhere. So this is pulse function, and at all other places except during the interval 0 to h, the value is 0. For t less than 0, it is 0. For t greater than h, it is 0. And for the time period between 0 and h, it is m. Okay. So this is pulse function, and we have seen the equation for this as this. So this is the equation of pulse function, f of t equal to m into u of t minus u of t minus h for t greater than h, and the Laplace transform is this. Now let us imagine I consider, or let me take the value of m as 1 by h. Let me take m as 1 by h. So I take an m as 1 by h. H is this interval. So if I take m as 1 by h, so I take an m as 1 by h is the same as this. Then if you imagine the limit h tending to 0, if you let h tending to 0, in the limit of h tending this h tending to 0, what will you get? We will get a function. If h tending to 0, this height becomes infinite. So we will get a function which is 0 everywhere, in the limit of h tending to 0, we will get a function which is 0 everywhere except at t equal to 0. So at t equal to 0, the value of function will be infinite. So let me repeat. If you let h tending to 0, in the limit of h tending to 0, you will get a function which is 0 everywhere except at t equal to 0, where the value of the function is infinity. Except at, this is not t equal to infinity, at t equal to 0. The function value will be 0 everywhere except at t equal to 0. At t equal to 0, the value of the function will be infinite. So this is known as impulse function. This function is known as impulse function. And the area under the curve with these values. What will the area under the curve? The area under the curve is 1 by h into h equal to 1. So even in the limit h tending to 0, when you get this function, still the area under the curve will be 1. So how does it look practically? And how do you visualize this function. So before we see how this function looks like practically, so let us try to write the equation for this from the pulse function equation. You know, this is a pulse function equation, right? And the impulse function can be derived from this equation. How? By, of course, we have taken 1 by m as 1 by h, and if we let h tending to 0, we are going to get impulse function equation. The symbol for impulse function, is del t. So symbol for impulse function is del t. So what will be del t? So del t is going to be the pulse function equation, which we wrote earlier, equation for pulse function, in the limit h tending to 0, right? So that is, let me write, limit of h tending to 0. What is the pulse function equation? 1 by h into u of t minus u of t minus h. I think this bracket is unnecessary here. Let me erase it. Okay. So this is going to be, so del t so equation for equation for impulse function is del t equal to the limit of h tending to 0 of pulse function equation. Since m equal to taken m, we have taken as 1 by h, and the area under the curve I said will be 1. Area under the curve will be 1 with the m as 1 by h. So this is known as unit impulse function. So this is known as unit impulse function, and the equation is this. This is known as unit impulse function, because area under the curve is 1. So we call it as unit impulse function. Well, now let us find the Laplace transform of this. So the Laplace transform of pulse function is this: f of s equal to m into 1 by s into 1 by s e power minus hs. I have taken m as 1 by h. You can recall from this previous lecture, Laplace transform of pulse function is this. Okay, pulse function Laplace transform is this. This is Laplace transform of pulse function. Now, since delta function, since impulse function, unit impulse function can be considered as the limit of pulse function in the limit h tending to 0. So the Laplace transform of impulse function can be considered as h tending to 0, limit of h tending to 0 of the Laplace transform of pulse function. So L of del t, L of impulse function, can be considered as L of ft in the limit h tending to 0. So this is L of ht, 1 minus e power minus hs by hs, limit h tending to 0. So if we substitute h equal to 0, what do you get? Numerator will be 0, denominator will be 0. You get 0 by 0, indeterminate. So you have to use L'Hospital rule. Let us use L'Hospital rule. L'Hospital rule. What is the L'Hospital rule? Differentiate the numerator with respect to h. So what will you get? Differentiate the numerator, differentiate the denominator with respect to h. So if you apply L'Hospital rule, differentiate the numerator, that is will be s into e power minus hs, denominator differential is simply s with respect to h. You're differentiating with respect to h. So now if you substitute h equal to 0, s and s cancels. So if you substitute h equal to 0, what are you going to get? This s and s will cancel. Substitute this, you're going to get e power 0 is 1. So that gives the result. That gives the result, namely the Laplace transform of unit impulse function. Laplace transform of unit impulse function equal to 1. Laplace transform of unit impulse function equal to 1. Now let us visualize how this impulse function can be approximated or can be visualized or can be considered in practice. We said earlier that impulse function is a function which is 0 everywhere except at t equal to 0 and at 0 equal to infinity. So we can practically visualize this as a function which suddenly rises to a very high value at t equal to 0 and immediately returns to the original value. Immediately, quickly returns to the original value instantaneously. Let me show this as a graph. So you can visualize this function as something which quickly rises to a high value at t equal to 0 and then instantaneously returns to the original value which is 0 in a short spell of time, in a very brief period of interval of time delta t. So this delta t should tend to 0. This delta t time interval, this here, should be 0. The function whose value quickly rises to a very high value at t equal to 0. For clarity, I have taken 0 slightly above on the y-axis and slightly to the horizontal on the x-axis. Just for clarity, 0 I shifted here, that's all. A function which rises at t equal to 0 very quickly and then within a very short period of time returns to the original value 0. This delta t, the time period in between, should be as small as possible. The limit delta t should be tending to 0. So in the limit delta t tending to 0, so this becomes the impulse function. So practically you can visualize this. This happens in many control systems. Suddenly some variable, some input variable like a flow rate, suddenly something happens, it quickly changes to very high value and instantaneously comes back to the original value. There is a very momentary disturbance, instantaneous disturbance, that's all. The disturbance doesn't last for a period greater than this disturbance does not last for any period which is greater than a short interval delta t. The disturbance does not last forever. The disturbance is very quick for a very short period of time. The disturbance takes place over a very short interval of time. So this can also happen practically. So in such situations we use this concept of impulse function. So this also has other names. It looks like delta. So it is also known as delta function. So it looks like a delta. So it is known as delta function. So impulse function or is also known as delta function, or it is also known as idealized pulse function because it is ideal case of pulse function, or instantaneous pulse function. So the common names are this impulse function or delta function. Why delta function? It looks like a delta here. It looks like a delta here. This function looks like a delta. So it is known as delta function. So impulse function and delta function are common names. Is also other names, idealized pulse function or instantaneous pulse function. So this is about instant impulse function. Now there is another point to be noted here. Yes, the impulse function is given by this equation, right? Impulse function is limit of h tending to 0 of u of t minus u of t minus h by h. If you look at this equation, this also tells me that the right hand side is nothing but the derivative of u of t. Right hand side is by the definition of derivatives, first derivative. This is nothing but derivative of u of t. So delta function can also be considered as the derivative of differential or derivative of step function. So this is another point to be noted. The impulse function or delta function is the derivative of step function. So this understanding this point, remembering this point will be helpful in many situations later on. Okay, so that is about this impulse function. What is an impulse function? It's a function which is 0 everywhere except at t equal to 0, and at t equal to 0 it is infinite, which is known as unit step function, and that is which is known as unit impulse function. That impulse function can be considered as same as pulse function in the limit h tending to 0, which means the impulse function can be considered as a derivative of the step function. And by this equation, we find that impulse function is a derivative of step function. Okay. And the Laplace transform of del t, L of del t is 1. And how does it practically look? A function whose value suddenly increases to high value momentarily and instantaneously is back to the original value 0. So it is known as delta function, looks like a delta, so it's known as delta function or impulse function or idealized pulse function. I hope you understood this. We'll come with more forcing functions in my next lectures. Please stand by those lectures. To be notified of these lectures, please subscribe to this channel. You will get more useful lectures. Okay, so stand by for more lectures on forcing functions. See you.